Hello everybody and good day to you. My name is Andrej Sepcic and this is the second part of the webinar which will be talking about the tan delta. Today we will talk more about the measurement process and the examples and some advanced knowledge. So we will today repeat what we learned and also we will show some examples, mostly on transformers, one example on cable, and in the end we will talk a little bit more about the advanced knowledge, and by advanced knowledge I mean some comparisons between PD and tan delta measurement with also polarization index, tan delta measurement, etc., etc. So without any further ado, let us start. There is 1 hour in front of us. So we can see right now what we learned the last time. Last time we talked about electrical insulation, of course, and we defined it as one or multiple materials which are non-conducting and provide electrical insulation of 2 parts at different voltages. And what we did then is we found out that we can model the insulation as a capacitor. And we spoke about the ideal insulation scheme or ideal capacitor and a real insulation scheme or a real capacitor. We can see that the ideal has just the capacitor and the real one has also the resistor connected in parallel. Now, after that, we learned that the resistive current is the reason why our insulation heats up, and that heat deteriorates the electrical insulation. So the IR, because it is in phase with the voltage applied, produces heat, and that heat creates a chain reaction which can lead to the damage of the transformer. Of course, we heard also some stories which tried to explain what is tan delta and how do we use it. So we heard the Dutch legend of Hans Brinker. It is a boy who saved the village by sticking a finger into a dike that protects, that insulates the sea from the land. And we compared the dike to electrical insulation. And then we also realized that in one example, a TV can function normally even if it's inside of aquarium, of course, if the aquarium is filled not with water, but with mineral oil. So if we want to check how clean that mineral oil, how much does it have, how much good are there insulating its insulating properties, we use tan delta to tell us that information. We also concluded after the first part of last time's webinar that to measure tan delta, we measure tan delta to assess the state of our electrical insulation. So tan delta tells us about electrical insulation, and we can also see, apart from that, if there have been some geometrical movements inside our, let's say, transformer. We focused on the transformer last time, we will focus also this time, but as we said in the point 7, we can test tan delta on many of the primary equipment. Wherever you have your electrical insulation, you can do a tan delta test. Then we defined what is tan delta. So tan delta is resistive current divided by capacitive current. So we can see that here. And if we express this currents in a different way, we can also reach the formula 1 divided with omega RC. What is R and C? Well, R and C are this capacitor and this resistor here. Then we also said that TD is equal to DF, or dissipation factor. So sometimes we say TD, sometimes we say DF. I mostly use the name TD. And we also defined a power factor. Power factor is very similar to tan delta. Actually, up to 10 degrees, they have almost the same values. And the power factor is used as a name and as a notion in some countries like USA, Canada. I also saw that being used in Vietnam, And in general, these two names are almost synonyms. So for example, TD and DF are synonyms, but TD and power factor are not synonyms because power factor is not IR over IC, power factor is IR over I total. But as we spoke last time, we said that this angle, delta, is very, very small, maybe 0.5 for some assets, 1, 2, or 3 degrees. And if you imagine this angle to be very small, then this line, which is the total current, will be very close to y-axis. And then this vector and this total vector will be very similar. So we can also put it like this. If these two numbers, tan delta and power factor, are not the same, then we already can be sure that we have a problem with insulation because this angle delta is very big. Very big, by that I mean more than a few degrees. So moving on, we discussed what makes the insulation deteriorate. So what makes it deteriorate? Well, first of all, it is water. For a transformer, we know that during the day it expands because it has more energy that it needs to transform. And during the night, since it transforms less energy, the volume of oil inside becomes smaller. So if it's expanding during the day and becoming smaller during the night, it's like a simulation of breathing. That way, the air gets into the transformer through the breather. And if that happens, even though we have in the breather some silica gel, which cleans the air from water molecules, still some pass inside and can make the oil more conductive. The second thing which can make the insulation deteriorate is partial discharge. So partial discharge are small sparks which can fly between the windings, between, let's say, parts of the winding and the tank, etc. Hopefully not the winding and the tank, because in that case we have a bigger problem. And partial discharge together with some other processes like thermal overheating can produce gas. So in the first step we have water, in second step we have gas. Both of these elements make the insulating material more conductive. And third is our general oxidation processes which create a sludge. Sludge is something that gathers in the bottom of the tank and it makes the whole insulating system more conductive. So in order to understand how much is our insulating system actually insulating and how much is it conductive, we do a tan delta test. Now, let's move on. What we did then, we spoke about the values of tan delta, which are acceptable values and which are non-acceptable values. In the table above, you can see that for a new transformer, we should have a tan delta below 0.5. That is a general rule. For some transformers, it's even less. For some transformers, it might be more, but this is a general rule. So 0.5. And then for service-age transformers, the tan delta should not be more than 1%. Now later we will explain these percents. Why do we express tan delta actually in percents? But what we need to have in mind is in general that if tan delta is more than 1%, it is the reason to do further investigations. You can also see in the table below that for extra high voltage transformers, these values are much below 1%, 0.5, 0.9, 0.8, and for distribution transformers, it's almost up to 2. So it is important, actually, we will see later, to have a record of measurement, to keep a record of measurement of tan delta to see how this number changes in time. Because sometimes you can be even above 1, but if it changes a little or not at all, then it still means that it is a good insulating material. Also, we spoke about the fact you can see that all these values are measured at 20 degrees Celsius. They are measured at 20 degrees Celsius because the tan delta is dependent very much on the temperature. So if it's dependent on the temperature, we also saw that if you measure tan delta at 70 degrees Celsius and we are measuring the temperature of the oil, in that case, in that particular case, that means that it is like 1% at 20 degrees Celsius. So we need to take that in mind and also compensate on the tan delta temperature wise. That is something which our test sets can do automatically. After that, we said what is the voltage and the frequency which we should use when doing a tan delta test. So first of all, we said that 12 kilovolt is a standard, especially for transformers. Sometimes for generators it is 15, but you don't need to go above 12 kilovolt because all polarization processes are done at 12 kilovolt. And that's very important to know. Even if you have a 400 kV transformer or 132 or 110 kilovolt transformer, you don't need to go above 12. Having said that, of course, you need to keep in mind that you cannot do a test at 12 kilovolt if the maximum voltage of your transformer is, let's say, 6 kilovolts. In that case, you will generate the nominal voltage of that transformer. So that's important to know. Maximum nominal voltage, or if it's more than 12, then generate 12. Also, very often during testing, 10 kilovolt is very much accepted value. What is the frequency which should be used? Well, that is a nominal frequency, 50 or 60 hertz. You can do a small delta between, let's say, about 0.5 or 0 or 1 hertz or 2 hertz plus or minus. That is possible, but not more than that. When we are testing on rotary machines, sometimes we need to go a little bit more than that, but as we said, that the formula for tan delta is 1 divided with omega RC. Omega is 2 pi f, so you can see that the tan delta does depend on the frequency. So we should keep that in mind. Also, we said that when our test sets are doing tests on the transformers, for example, we actually never do absolute 50 in order to avoid the noise. So we do it at 50.5 or 51, and if we do it at 50.5, we also do it at 49.5. So it's symmetrical test where we do it twice, 50.5 and 49.5, or 51 and 49. Then we started talking about the exact process, how to measure tan delta on a power transformer. So the first step was to de-energize and disconnect and de-energize the power transformer, because this is an offline test. By de-energize, we mean that with a grounding rod, you need to touch every phase to make sure that all the energy is out of the transformer. Then the second important step is to short circuit. As we can see, we have short circuited the primary side and we have short circuited the secondary side. And when you do this, you create an equivalent scheme with 3 capacitances. There is a capacitance high voltage, low voltage. There is a capacitance high voltage ground, and there is a capacitance low voltage ground. That way, you can measure 3 capacitances, and at the same time, when you measure capacitances, you measure tan delta, because we said that the tan delta is basically telling us the equivalent scheme of our insulation. What we need to do after that, we need to ground the test set and connect the cables. And then we have to set up the measurement in the firmware by choosing where have we connected the generation, the high voltage generation of our test set, and where have we connected the measurement. And then we should choose the voltage and the frequency. After we choose where have we connected, we can also choose what do we want to measure, and automatically the method of measurement, we will be talking about the methods later, will be also chosen by us. Excuse me, automatically. This is what it looks like when we are in the field. So we would, for example, connect on the low voltage side, the generation and the measurement on the high voltage side. This is the case when we want to measure CL. In this case, we measure CL, or we can measure CHL, and if we connect the generation here and the measurement here, then we can measure CH. In general, we need to measure CL, CH, and CHL in the course of measurement. First, we will have generation on the high voltage side, then we will end the measurement on the low, and then we will switch and put, like here, generation on the low voltage side and measurement on the high voltage side. After we have measured the capacitances of the body of the transformer, what we will be doing is we will be measuring the bushings. So when we go to measure the bushings, we need to remove the short circuits because we measure each bushing by itself. So phase A, phase B, and phase C. And we measure C1 and C2. We need a tap adapter. We need a measurement point for the bushing measurement. And that measurement point is usually located in the bottom of the bushing. If there are no bushings, sometimes you can also use a hot collar, and if you're doing that, you need to clean the insulation of the bushing properly. So this is how we do the test on the bushing. This is C1 from the top of the bushing all the way until the tap, and then from the tap to the ground. This is what it looks like, the bushing. And we can generate 12 kilovolts if this is our nominal voltage is more than that, and very often 10 is the standard in that case. When we are measuring C1. When we are measuring C2, what we need to do is to generate less. We need to generate less because this is quite close to the ground, and even with 1 kilovolt, it is more than enough to do a test. In the end, we will have our set of results, and we need to evaluate them. Do we have good results? So we can do a comparison to the previous values, or we can compare them to the allowed values. Allowed values, by that I mean the table, or we can connect them between themselves. If we have bushings, they all should have more or less very similar values. If we test the cable, the phases should all have very similar values. Or we can compare these values to an asset working in similar conditions and having a similar structure. So these are the ways how we can evaluate if the results are okay. If we have some suspicions that the value of tan delta is not okay, we can do a voltage or we can do a frequency sweep. Frequency sweep can be done on a bushing, is usually done on a bushing, and voltage sweep is done on the body of the transformer. Another option is if we really see that there is a problem, we can install the continuous TD monitoring. That will give us a better insight of how the TD changes in time. And this is where we pick up now. So we did a short introduction, and what we are trying to do here is to explain a little bit better. When you do a tan delta test, you get a lot of numbers, and these numbers give us a lot of meaning, a lot of information. So we will try to explain right now how can you interpret those numbers. The set of results is the voltage which we generated, the current which was generated with this voltage. So we can see that this is 12.855 milliamps. The capacitance which we measured is actually the equivalent capacitance here. The tan delta, this is the tan delta which was measured. The power factor and tan delta have the same number, and the resistance RP connected in parallel. These two values we can use to calculate tan delta, and that's what we did here. We said tan delta is 1 divided with omega RPC, and when we put in all the numbers, we got the same value, 0.228, as the tan delta. Also, we get the angle phi, which is ideally 90 degrees, but now it's 89.8692, and if we deduct from 90 this number here, we get the angle of delta. So this is the delta, and in this case, the delta is 0.1308. We said last time, if the delta is more than 0.57, then the tan delta is more than 1%. And in our case, the tan delta is the delta is 0.13, and the tangents of that is 0.22. Moving on, we get some more results. We also get the RS, which is the resistance, if we were to make the equivalent scheme and connect the resistance in series, this would be the resistance connected in series, and we can also calculate that through a formula. And the QF, the quality factor, is a reciprocal value of tan delta. It needs to be bigger than 100, so it's 437. So these are the results which we get when we do a tan delta test with our test sets. And here we want to say, why do we express tan delta in percentages? Well, first of all, tan delta is a non-dimensional number. You have amps divided with amps. And since it's a non-dimensional number, you can multiply it with a certain number, in this case with 100. And we do it here simply because these angles, as you can see, this is more appropriate representation of delta, are very small. So if we have the delta of 0.1 degrees, the tan delta will be 0.00175. But if I multiply it with 100, I get 0.175. It's simply easier to do that than to mention every time 0.00. In this case, it's 0.175, and for 0.5 degrees, instead of saying 0.00872, we just say 0.872%. So that is the answer to the question, why are we expressing tan delta in percentages? It is to make an easier explanation. It is to make an easier distinction. It is to make it basically easier to communicate these informations amongst ourselves. You can choose in our test sets whether you want to have an absolute value or you want to have a percentage with tan delta, and the only difference is multiplication with 100. Now, in this slide, I would like to give you an idea, because we said that you can measure all kinds of insulating properties on all kinds of devices. And let's see how does the capacitance change from one device to another. So power transformers are in our focus, and we can see that the power transformers have the capacitance between few nanofarads and few tens of nanofarads. Then the bushings on the power transformers have even less capacitance. You see, capacitance definitely depends on the size. The capacitance of anything depends on the size, because if something is bigger, then you can put more electrons inside, and then it has a bigger capacitance. So bushings are smaller, so they have a smaller capacitance, only a few hundred picofarad. Rotative machines can be big, and they are big, so they can have from few hundred nanofarads to few microfarad capacitance. And then we have cables. Now, depending on the type of the cable can be long, can be short, can be medium voltage, high voltage, can be XLPE, can be insulated in oil, all types of cables. We took one example here. For a 20 kV cable in XLPE, we can have 0.36 microfarads per kilometer. So for 1 kilometer, 360 nanofarads would be a capacitance, which is not a small number. Moving on, we are now ready to see a video. Now, during this video, I will not talk, simply because the explanations are already in the video. And you will see how do we prepare in our firmware, step by step, the measurement of tan delta. Just be careful and follow screen. So let's see how we set up the measurement of tan delta in power transformer. As you can see here, and as you could have seen before, we measured the 4.45 picofarad capacitance on a small sample, and that made us understand that tan delta was 1.26, which means that we have a problem with that insulation. So moving on, now we have some examples, and let's see them one by one. Example number one is the measurement of tan delta on a transformer in Kazan, Russia. We measured 3 parameters in this iteration because it had primary, secondary, and tertiary winding. So the primary, CH, the first value we measured was capacitance between the high voltage winding and the ground, and we had tan delta of 0.2283. Actually, this is the example we used before when we were explaining what numbers do we get when we are explaining when we are doing the tan delta measurement. Then we measured CHL, capacitance and tan delta between the high voltage and the ground, high voltage and the low voltage. We said that very often this is the most important value when we are measuring because it is between high voltage and low voltage, and if something breaks there or if there is some imperfection there, there is a tendency that this will break quite soon. The tan delta was 0.2518, much below 1%. And the capacitance was 3.2. The third value was CHT, capacitance between the high voltage and the tertiary. We also got a good number, 0.2447, and the capacitance was 3.1983. As we said, sometimes some procedures require then to measure the sum. Basically, you just change the value, the mode of measurement. We'll talk about that later. And then we measure CH plus CHL plus CHT. I wrote here the CH value, the CHL value, and the CHT. And then I summed it all up, and I got 10.5086. The measured value was 10.5077. There is a very high accuracy of 0.01%. There is a very small difference. It's 1.1 picofarad. So this is how you would normally do. The next step here would be then measuring the CL, low voltage ground, and CT and CLT, low voltage tertiary, and then CT, the tertiary ground. And then you would have all the values. In this next example, also done on a transformer, this transformer had only primary and secondary. It did not have the tertiary. So what we have here is the measurement of CHL, and we got 0.18, even better than before, and the capacitance of 7.8. It was done at 10 kilovolts. And then we did CH. Basically, we just changed one drop box in our firmware to do this measurement and then to do this measurement. We didn't change the connections. And just observe, we did this with the method USTA, and this was done with the method GSTA. When you say what capacitance you want to measure, this is what changes. So now we have the measurement of CH. It's 0.2185, much less than 1%. So we can see that all these insulations are in good state. The capacitance is 8.15 CH, and we can see CH, CHL, the sum of the capacitances, and the measured sum of the capacitances is 15.98, and it is the same as the sums when you sum them up with a calculator. So also in this example, by measuring two capacitances, by measuring two transformers, we saw that the tan delta was pretty good. It was never above 0.3%, and that's good because this was a high voltage transformer. Example number 3 was done on a bushing. Now in this case, we found issues on the bushing. As we said, when you are measuring the bushing, you will have to find the tap adapter and connect the generation up on the top of the tap adapter, and the measurement should be connected here to measure C1, and then you should invert that to measure C2. You should put the generation here and the measurement on the top. We saw that tan delta, which we measured here, is 2.73, And this is already showing us that we have some issues. So 2.73 tells us that we have a problem. This was done on phase A, and we decided to do a sweep. Usually on the bushings, you need to do a frequency sweep. In this case, first we did a voltage sweep. We did a voltage sweep just to assure ourselves that the capacitance should stay the same, and it did. 146 picofarad was measured all throughout, and we saw that the tan delta was changing. But then we did the frequency. So after voltage sweep, and what is a voltage sweep? A voltage sweep means that we will do a test at 2 kilovolts, 4 kilovolt, 6 kilovolt, 8, 10, and 12. The capacitance should stay the same. Tan delta ideally would change a little bit, but this time it changed more. And then we decided on phase A, again, to do a frequency sweep. We kept the voltage the same, 2 kilovolt all the time, but we changed the frequency. You see, in the previous test with the voltage sweep, frequency stays the same, but the voltage changes. Here the voltage stays the same. We change the frequency, 20, 35, 50, 135, 220, 305, and 400 hertz. And what we found out is that the value starts with 5 of tan delta and drops to 3, and then 2, then 1, and you can see how it drops right here. We get this curve, and this is the sign that something is not correct with the insulation of this particular bushing. So we went to bushing of phase B. On phase B, we got slightly better results. We didn't go like 5 or 3, the maximum was 1.8, but still, what happened is that we got this type of curve. This was on phase B. The capacitance also stayed the same, about 146 picofarads. And then we did the same test on phase C. The results on phase C were also similar to phase A, almost 5, then 3, then 2, but it drew this type of curve. The frequencies in every test are the same. And the last test we did was on a neutral. So on a neutral, because this was a YN winding, we got 10 as the first value, and then it started going down quite a lot. It drew the same characteristic, and this proved to us that we are dealing here with a very problematic bushings. So all bushings, A, B, C, and neutral, had issues. We've proven those issues with the measurement on not just one frequency, but multiple frequencies. And after that, we had to do some action. So, but before I tell you what we did, let me explain to you why do we see this type of curve and not a straight line? Because normally we should see something like this. This should be, something like this should be the result. But we see something which is big and then it becomes very small. Why? If you look at the tan delta value in frequency, this would be the normal characteristic. You see the one which starts from y-axis. So it would go like this, and this would be our 50 hertz. So from 50 hertz on, if you increase the frequency, you would get to these values, you would get this type of curve. You see, it is a little bit bigger in the beginning, and then it starts to go up a little bit. But as the water gets inside, as the insulation becomes more degraded, this whole curve shifts to the right. So shifting the curve to the right creates now a different presentation. If we say this is 50, we will not see anymore this, but we will see the curve going down and then the curve going back up. So we will see this and this. And because of that, you don't see more or less a straight line. You see something going down, and then you see something slightly either going up or staying the same. So because of this, we know that we had a problem with our bushings. What we did, all 4 bushings were changed, and then the values, the test was repeated, and all the values were shown to be normal. So we need to take into consideration that if the value of the tan delta is suspicious, like too big, on the body, we will do the voltage sweep, and we would expect a straight line. If we get a line which changes and goes up and then down, or down and then up, then we have a problem. So also let us say that when we talk about bushings, we will do the frequency sweep, and in case on the bushings you don't have a tap adapter, you might use a what we call a hot collar, which is like a strap which you put around the bushing, around the bottom of the bushing. You need to clean the bushing before doing that, but also in that case the interpretation of results will be slightly different because 1% will probably not be reached, the values would be somewhat high. So this was the example which spoke about bushings. Now here we have one example which is a very short one, and we talk about cables. So for cables, the value of tan delta must be even lower than 1%, especially XLPE cables. In some cases it's 0.1, in some cases it's 0.5, depending exactly on the voltage level and on the type of the cable. In this case, what we did is we generated the voltage onto the conductor. This was about 100 or 200 long cable, which we tested in Turkey. And the measurement is connected from the guard, so from the shield. We need to do a test in GSTg A plus B mode. You will understand what is that in just a few minutes. And the number which we've got is 0.013%, which is a very small number, and that's a good number for a cable. So you can also do a cable test. Of course, it depends on the length of the cable. If it's few kilometers, then maybe we will not be able to charge fully the cable, but if it's few hundred meters, probably yes. Now let us discuss what we spoke about before, UST and GST modes. So what's a UST mode? What's a GST mode? Let us see how does that reflect on what we are talking about today. UST is short for ungrounded specimen test, while GST is short for grounded specimen test. So UST and GST. And there is also GSTg, grounded specimen test guard. So guard means that some currents which we measure are not actually taken into consideration. So let us explain step by step what we mean by specimen. Specimen means a part of insulation. We could also say capacitor, because you saw that we don't have one measurement for tan delta. We have CH, CHL, CL. We have minimum 3 measurements. So there are at least 3 parameters describing this particular transformer. So what we are saying here is instead of specimen, we can also say capacitance. And also, the good thing is to have as much specimens as possible, because when we do certain tests, if we can focus and zoom in on a certain part of insulation and understand where the problem is, that can help us in understanding how to also fix the transformer afterwards. So let's see the equivalent scheme of a transformer which has a primary, secondary side. We have 3 specimens, CH, this one, CL, this one, and CHL. We can see that this will be measured with an ungrounded specimen model, since it's not touching the ground in any point, and these 2 will be measured with a grounded specimen because they are touching earth at one point. So this is GST or GSTg, and this is a UST. If we have a transformer with primary, secondary, and tertiary side, then we can see that we have 3 specimens which will definitely be measured with the GST or GSTg mode, and we have other 3 specimens which will be measured with a separate UST mode, because UST means they're not touching the ground. By the way, all this, you don't have to know anything about it. Our test set chooses automatically which method it needs to use. But still, I wanted to educate you in the future, if you wanted to know a little bit more, to understand what is a UST and what is a GST. So in order to have a better resolution, as we said, it's a good idea to test the smallest possible sample. So we have a better chance to see the influence of a small imperfection. So we can zoom in on a separate segments of insulation. We can zoom in on CH or CHL or CL. Now, in a 2-winding transformer, we have, as we said, CH, high voltage to ground, CL, low voltage to ground, CHL, high voltage to low voltage insulation. we have C1 inside the bushing and C2 between bushing and the tap. And let's have one example. If we measure a standard transformer, by standard I mean primary and secondary side, and we get these results. CHL has a tan delta of 0.75, CHL. CL has a tan delta of 0.56, and CH has a tan delta of 0.98. C1 is 0.55 and C2 is 0.62. In this case, this might present a problem because CH is very close to 1%, and the higher voltage, which has a worse insulation, can present a bigger problem. So a higher voltage, which is this one here, if it's close to 1, presents a bigger problem than if a lower voltage, for example, is close to 1. Now, of course, even if a low voltage can also discharge, but the biggest problem would be if we had a CHL at 0.98, that would really present a problem, and we would have to do a voltage sweep then, and maybe some additional tests like partial discharge, etc., etc. So let's see. Let's go to the modes of testing to understand what is actually this. So we should keep in mind next. Imagine you have a switch inside the test set, and this switch chooses which currents it wants to measure. Because when we are generating voltage, this voltage generates currents. There is a current flowing through here, there is a current flowing through here, and we choose which currents we want to measure, because the currents we measure are the capacitances that we measure. If we have a transformer with primary, secondary, and tertiary side, we will not just use input A, but we will also use input B. So inputs A and B will be used. And then we will have, and we should keep in mind, we always have 3 measurements of currents: input A, input B, and ground. Always also the ground. That's why we have to ground the device always properly. And this is a very important table which shows us actually how do we do the measurement, or what does the USTA means, and the other ones. USTA means just measure the current on input A. So just that current will be taken into consideration. USTB will mean just measure the current on input B. And USTA plus B will mean measure the current in A and measure the current in B input. So this will be the sum of 2 currents. So that's a UST. There is no ground current measured in a UST. Then we go to a GST. GST means measure all currents on input A, on input B, and on the ground. GST GA, ground specimen test guard A, means measure all the currents, but avoid the current on input A. You see, we don't measure input A. GST GB means measure all the currents, but the current on input B. As you can see, we don't measure the B. And GSTG A plus B means measure all the currents, but, measure just the current in the ground. So we can say UST will never measure the current on the ground, GST will always measure the current on the ground. And if we take this example, another way how to say this is that when we explain UST, we say which current do we measure, which current do we want to measure. USTA, we measure input A, USTB, we measure input B, and USTA plus B, we measure A and B inputs. But with the GST, excuse me, we have to say which currents we do not measure. So GST, we measure all. GST-GA, we do not measure A. GST-GB, we do not measure B. And GST-GA plus B, we do not measure A and B. So we just measure the ground current. And this is another way of showing how different methods are used when measuring on a transformer. If we want to measure CH, obviously it's touching the ground, we need to use a GST-GA method, automatically chosen by the system, generate on the high voltage winding and measure on the low voltage winding. If we switch and generate on the low voltage winding and measure on the high voltage winding with the same method, we will measure CL. CHL can be measured from the high voltage and the low voltage side, and it will use a UST method because it is ungrounded. It is not touching the ground at any point. And if we measure CH plus CHL, if we want to measure these two capacitances, we'll use a GST, and we can either connect to the high voltage and measure on the low, or connect to the low and measure on the high for CL plus CHL. C1, also nothing touching the ground, we use a USTA, generate on the top of the bushing and measure on the tap, and C2, we generate on the tap and measure on the top of the bushing using the GSTGA method. So let's just do a little bit more in-depth look and see if we do a standard measurement on a standard transformer like this, how does this now reflect itself onto our system. If we say in our system that we want to generate on the high voltage winding and we want to measure CHL, the system will automatically choose a USTA method. That's one thing. Now, in that case, what is happening inside is this. I'm generating a voltage on the high voltage side, and that voltage creates a current which runs through the capacitance CHL and goes to the input A. There is also a current running through the capacitance CH and going into the ground, but because I'm using a UST method, I'm bypassing this measurement. I'm bypassing the measurement of the current running in the ground. I'm just measuring this current, and that means I'm just measuring CHL. So you see, with USTA, by definition, I'm not measuring ground, I'm just measuring this. I'm entering the ammeter and I'm measuring just the current running through CHL, so I'm just measuring CHL. If I want to do a GSTGA measurement in the same setup, I generate on the high voltage side and measure on the low voltage side. What I do is I say I'm generating on the high voltage side, I want to measure CH, and automatically it pops up GSTGA. What does this mean right now? I'm generating on the high voltage side, and then since I'm doing a GST measurement, I'm also can measure the ground and I can measure the input A. But since the measurement is GSTGA, so I'm not measuring A, what actually happens inside is that the current coming to the input A is not taken into consideration. As you can see, this yellow line bypasses the ammeter, and I'm just measuring the current running through the ground. Actually, I'm just measuring CH. And that's what we wanted to have. We wanted to measure CH, and because we wanted to measure CH, we measured it here. We didn't measure the current running through here. Otherwise, if I also measured this current, I would be measuring CH plus CHL. And let's see, one more example. Here, we are now doing the measurement of CL. On the low voltage winding, I'm generating, and I'm choosing which capacitance I want to measure, CH, L, CL, or CL plus CHL. I choose CL, and I'm doing the same thing as before, generating here and only measuring this current. Even though that this is connected, I'm bypassing. I'm bypassing and just measuring the ground current. So by changing the place where we generate from high voltage to low voltage of the transformer, we change from measurement of CH to CL. That's another answer to the question why we have to do some change in the measurement, some change in the generation when we are doing the measurement. We cannot do everything from the high voltage side. And this is the explanation of what is a UST, what is a GST, and this is now an explanation why do we have inputs A and B. We actually have inputs A and B on our measurement system, because if you have a transformer with primary, secondary, and tertiary side, then you need two inputs. You can generate on the high voltage side and measure from the low voltage and the tertiary, for example. And then you would move the generation from high voltage to low voltage, and this measurement would go here. And then the last one would be generating on the tertiary, and the two measurements would be on the high voltage and the low voltage side. So this is the explanation of what is a UST and what is a GST. I hope you find it understandable. We have just a few more minutes and then we will finish up. I just also want to address another important point, and that is why is tan delta better than polarization index, the DC method. So first of all, what we understood is that the tan delta gives us more repeatable results. If you do 5 tests of tan delta, you should get the same number. With the PI, you don't do that. You don't get the same numbers. Also, the tan delta, which is very important, doesn't leave a lot of free electrons in the insulation, because if you had some voids in the insulation, the free electrons can trigger a PD activity, which is definitely not good. So the tan delta is less destructive than the DC test. Also, tan delta is a faster test, because with the PI you need to measure for about 1 minute and then 10 minutes. And with the AC, since we use our equipment on AC voltage, it is a more similar condition. So that's why we love AC, because it is really doing the test with the situation which we have when we run our asset normally. And of course, it is time independent. AC you can measure for a long period of time, I mean tan delta, and the DC changes in time. Another point I wanted to make clear is the similarities between TD and PD. So first of all, PD, or partial discharge, are micro sparks which partially bridge the insulation. So while TD is more like an overall statistical value of the insulation's conductivity, of the whole piece of that sample. Tan delta also shows us the overall state of insulation, while PD is showing us if we have some issues happening right now. So if you can have a situation when there is no PD, and then a situation when there is a PD. I mean, you can have a situation where there are no sparks flying inside the insulation, and later the sparks might fly because of over voltage or because you are moving OLTC or something like that. Also, and that is also explaining the point 3, you can correlate certain activities. So when you correlate certain activities, that shows you practically how, by correlation, you can see what causes some abnormalities inside of your transformer, generator, motor, or cable. Also, the best solution for properly maintaining not just the transformers, but all asset is continuous monitoring. We had a lot of webinars on the topic of continuous monitoring. We will have them again. And we are now also implementing the continuous. We already did that on medium voltage cubicles, because on a medium voltage cubicle, you can monitor not tan delta, but for example, temperature and partial discharge. So soon we will have some webinars on that topic. And the last point, PD is better seen on bushings, which are very prone to deterioration. So when we test actually transformer for PD and TD, we put our sensor on a bushing, because the most sensitive part are those bushings. And if you find a PD there, you would want to be the closest possible to the most to the device, to the part of the transformer which is the easiestly damaged. So this part of the transformer is the most delicate one, and since it's the most delicate one, it needs to be properly maintained and monitored. And when the measurement is done, you have to measure exactly there. So these were all the points which I wanted to make today. We spoke about what we did last time. We spoke about the examples on the transformer and on a cable. We spoke about the TD, the methods of measuring the TD, the grounded specimen test and the ungrounded specimen test. We believe that you gained some knowledge, and let me check right now if we have some questions so that we can answer. So Mr. Abid is asking, in the case of negative TD, let me see. Okay, sorry, yeah, I just forgot, this wasn't the last slide. The last slide is this one. So we can see that the negative tan delta is also the thing which we wanted to talk about. We were often asked about the negative tan delta. So the negative tan delta is something which can happen in few occasions. So if the connections are not done properly, if the test object and the device which is testing it are not grounded at the same point, if we put some special additives, for example, in the oil of the transformer. And the last question is, maybe the negativity is due to the inaccuracy of measurement. If the negative value is very, very small, then probably that means that we are at 90 degrees, and due to the inaccuracy in measurement, we are exactly where we want to be. So this is a good value. So if it's just slightly over 90 degrees, that's fine. Or if it's a little bit more over 90 degrees, check your connections to the ground. And if you've put some additions in the oil, check again. Maybe this will give us a better idea why do we have a negative tan delta. So by doing this, I want to thank you for your attention. A whole hour has passed, and it was really, really nice spending time with you. I want to thank you for your attention, and I call you to contact me if you have any inquiries, if you are new to tan delta and would like to have some more knowledge. This webinar will also appear, so good luck with your tests, good luck with your personal growth, professional growth, and stay tuned for more webinars which will be coming up in ALTANOVA. Thank you for your attention and have a beautiful remainder of the day.